buddy. What you doing? What's going on, mister? Flop. Hi, Casey. Have any questions for me? Let me know if you can hear me okay. Bigger. Hello, can you guys hear me? P orbital and pi orbital. So, let me type this in. Oh, also, there's like a 20-second delay between when I talk and when you hear me. So if it doesn't seem like it's synced up perfectly, that's because it takes time to transmit data through the internet. So I think you mean a pi, P-I, like the Greek letter pi, not P-I-E. So a p orbitals, when we're talking about atomic orbitals, right? We have s, nds, p's, f orbitals. But when we get molecular orbitals, like two atoms form a covalent bond, they form a new type of orbital, and those we have as sigma orbitals and pi orbitals. So one is an atomic orbital and one is a molecular orbital, meaning one's part of just an atom and one's part of a molecule. Easy questions like that are great. Let's just keep doing those. Who else is here? It says there's 3 people watching. I see Casey. Are there other questions? Hello?
Hi, this is your callback from Google. A specialist is on the line ready to help you from here. Just so you're aware...
Guys, hold on just a second. I'm sorry. I've been on hold with Google for a while. Hi. Yeah, you are. I just need... Guys, sorry, hold on just a second. I'm like multitasking right now. I got a new phone in today. It got shipped to me because my other one broke. And it said to follow the directions, I think on the shipping label or something, but there weren't any directions on how to send the old phone back.
Okay, so
Was there supposed to be like a shipping label or something?
Okay, did you, is it, the
there was no shipping label other than the one on the box.
Yes, you send it back to the same one.
So do I just cross out the to and the from and put to and from on it again?
Just give me one moment. Give me one moment. Yeah, you'll just put to just the same as the label, then from you.
Okay.
Your address.
Okay. And am I paying the postage on that?
Are you paying the postage?
Mm-hmm.
Okay.
Like, there's no label to put on there. Do you see what I'm saying? Like, there's not like a pre-printed label to put on there. It didn't come with one.
Okay. All right, give me a moment. It should have, all right, let's see. Megan?
Yes,
Okay, the shipping label is, in your email.
Oh, okay. So I'll just print it out then? I'll look for that email. I didn't see it.
Oh, it's okay. It's going to be for September 17th.
Okay. Thank you so much.
Okay. You're welcome.
Mm-hmm.
Would you like to do a Google survey for our interactions today?
Well, I'm actually kind of in the middle of something with my class right now. I'm a college professor, so I kind of need to go, but I'm sure they're happy to say hi to you. So,
Okay.
but thank you.
Okay.
All right, bye.
You're welcome. Have a great day.
You too.
Bye-bye.
All right, sorry about that, guys. I'm so sorry. Oh, goodness. Okay, so Alyssa, we actually didn't get to, oh, wait a second. This was labeled Organic 2 review session. It is? Oh, look at that. It just saved it. Here, let me see if I can, brief organic exam 1 review sheet session. I'm sorry, I totally didn't realize that would save the name from my class the other day. I don't know if that'll change it in time or not. Shoot, hold on, let me pull this back up. Okay, so since some of you guys are watching this now, it says there's 6 of you watching, I just wanted to tell you a couple things. Number one, there's about a 20-second delay. You guys can ask me questions and I can type back pretty much instantly, but the actual feed and me speaking and everything that's on the video takes about 20 seconds to go through. And that kind of depends on your computer and I think how far you are from me and things like that. Another thing is that I have to have about 6 different screens open to do this. So if you are wondering why I keep bouncing around and having these kind of strange pauses, it's because I'm having to pull up different things. Okay, so that said. So Casey, yes, issue with Sprint. Special issues, right? Isomers, generic term. Sarah said she was confused why this video is Organic 2 review session because I messed up and didn't change the label. because I've been waiting on the phone with Google for an hour. And then Alyssa, how do you know what side is favored in the equation based off the pKa? So Alyssa, we actually haven't covered that yet. I kind of skipped over that, but basically, if you want to know how, you go and you favor the side that makes the weaker acid. So if I have, let's say, hold on a second. Let me do a reaction for you. So let's say I have, takes a while to draw on Chem Sketch, guys, I'm sorry. Okay, so let's say I have this carboxylic acid, just kind of a weird random carboxylic acid. And then I wanted to react that with some sort of, let's do a strong base to make the reaction pretty easy. So let's just do some hydroxide. Okay, so what I get from that, stretch this out so you guys can actually see it. Oh, and let me know if you can't like see anything, if what I'm doing is like too small or something and you can't see it, because I can make things bigger to a certain extent. Okay, so in this type of acid-base reaction, I'm going to deprotonate the carboxylic acid. Why is that not? Let's try that. There we go. Okay, and then I get water. As you guys are all well aware that anytime we have hydroxide in there, you're basically going to get water. Okay. So the question then is, how do I know which side is favored? Okay. Oh my goodness, let me turn that off, I'm sorry. And so if I'm looking at pKa values, the one for the carboxylic acid is about 2 to 4. Hydroxide doesn't have one because it's not any kind of acid, right? Water is about 15. So which one is the weaker acid? Water, okay? That would be the conjugate acid in this situation. So we've labeled these things before: conjugate acid, weak acid, conjugate base, right? The hydroxide is a strong base. So we've been able to do that before, and the question is, how can we tell which way the equilibrium would favor? And you always favor the direction of the weaker acid, okay? Most chemists would say the weaker acid-base pair, but for all intents and purposes, for us, it's always just going to be the weaker acid. So hopefully that makes sense to you. If not, let me know. We didn't cover it, so I wouldn't expect you to have that information. With the higher pKa, that's right. As long as it's your acid. So you have to look at the weak acid and the conjugate acid. Because you've probably seen some examples where, you know, the base actually could also be an acid provided, like water could be an acid or a base, right? So you just have to kind of make sure you're looking at the weak acid and the conjugate acid for a reaction. Who else do I have here? Got Casey, Alyssa, and Sarah. Hi. A few others that are being quiet. Yeah, so Sarah, that's actually something that Casey asked. Let me scroll right up here. I think you can actually see it. Yeah, she asked it right there. So at the very beginning of the video, I actually talk about it. So p orbitals are atomic orbitals, right? You've got s orbitals, p orbitals, d orbitals. But then a pi orbital and a sigma orbital, those are molecular orbitals. So those are what happen when two atoms come together and they form a new orbital to form a covalent bond. And yes, a pi orbital would be made out of two p orbitals. That's correct. There is a sigma bond there, Casey. And I can draw that with this program if we wanted to, if you wanted to show it like that. But you don't have to because it is assumed that it's there. Oh my gosh, they're sending me. And so also, if you notice, there's other hydrogens here that we're also not showing, but that doesn't mean they aren't there, right? They're just assumed. Why is... Let me minimize this window and try and pull it back up. I don't know why it's got all these weird little boxes around everything. The thing that we're doing tonight is very taxing on the computer. It requires a lot of my RAM. And so sometimes it does weird things. So Sarah, when I'm counting sigma bonds, do you count the bonds between carbon and hydrogen? I don't know, are they sigma bonds? If sigma bonds are always the first bond made, then you'd have to count them, right? It would be all of the first bonds. The only ones you don't count are double bonds and triple bonds, but you'd still count the one sigma bond that's between the double and triple bonds. Can we do an example of a resonance structure? Absolutely. This ChemDraw program is being kind of finicky right now, so I'm going to switch over to the paint. We can do it on here. So let's do... My drawing on a computer touch screen is even worse than my drawing on the board, so I apologize. It's a little pickier. That's supposed to be 3 lone pair. They're looking kind of special, but I'll just take them off. Okay, so what would be a resonance structure for this molecule? Go ahead and work on that for a second. Melissa, I'm not sure exactly what you're asking me. Are you asking me a question? I think I'm one of the tests where there was an acid that was NH3, and if asked of the 5 acidity factors, which one did it have or which ones did it have? Can you try again? I'm sorry, I'm not sure what you're asking me. So I'm going to go ahead and finish this resonance structure for Nicole. So electrons can move in here between the oxygen and the carbon. The bond here can come out onto the carbon. So if we start with a lone pair on oxygen, you're pretty much always going to get a lone pair on something else, right? Otherwise, you wouldn't be able to have conservation of charge very well. Supposed to be a negative charge, sorry. The drunk squad. Who is the drunk squad? Oh, Lordy. Oh, and also, Nicole, we could do another resonance structure here where these could come in and those could come out. So if you have something you must be a proud wife. Oh, Lordy. Let's see. So, Nicole, if you also had something like this, that would be also a resonance structure. There would be 3 resonance contributors for that molecule. Okay. Alyssa, you didn't get back to me yet. Sarah, yes, check. Alyssa, not pertinent amines. Can you guys give me a more specific question? I'm not exactly sure what you're asking me. I'm sorry. I might be dense or something. Are you just asking for like an example on how to tell how many different factors are contributing to its stability as an acid? I can do a question like that. I'm just not sure that's what you're asking me for. Like, if I have, oh shoot, hold on. Oh, actually, let's do this example. Well, so let's say I have a protonated amine. Oh, and FYI, I'm with you guys until 7 o'clock tonight, but then I have to hop off. I have a dinner date with a friend whose birthday's today. Okay, so let's look at this molecule. It's called methylamine. And we're looking at this as an acid. We know the pKa for an amine is about the 8 to 10 range, okay? And if we lose, let's see if I make that, that's way too small. Okay, let me just scoot over here a little. So if I undergo acid-base chemistry on that, testing to multitask myself. Well, as you just saw me on the phone with Google, I'm kind of in the same boat, Alyssa. Don't feel too bad. Okay, so here I have my weak acid and a conjugate base for that. Now we could use any base to do this reaction, but the question is, why would that protonated amine have kind of a low pKa value, right? Because 8 to 10 is comparatively low, especially compared to its conjugate base, for example. So let me ask you this. We have 5 factors that we can consider, and I think I can actually type these on here. Let's see. So number 1, electronegativity. Wow, yeah, okay. Inductive effects, resonance, size, and which am I missing? Charge. Okay. So if those are the 5 factors that I'm kind of taking into account, trying to figure out why something would have a low pKa, you're essentially saying which of these forces will stabilize it when it loses a proton. Okay, because in acid chemistry, that's what we're essentially looking at. So, okay. Sorry if my screen bounces around. I try and hold it while I'm doing this. So, okay. What I want you to do is ask yourself a few of these questions, and I'll go over the answer too, but I want you to think about it first. So, you have these 5 factors: electronegativity, inductive effects, resonance, size, and charge. And we're looking to see, because all 5 of those are stabilizing forces, right? So are we putting a negative charge on an electronegative atom? Yes or no? Did we put a negative charge on the nitrogen? The answer is no. Inductive effects. Is there another polar bond somewhere, like another electronegative atom, like fluorine or chlorine or oxygen or nitrogen, somewhere else on the molecule, not connected to those hydrogens, that could influence the electronic character of the molecule? If I look, the only other thing on there is a carbon. That is not on our list of electronegative atoms, right? So that one wouldn't count either. So let's like say, no. This is kind of fun. Resonance. Do I have resonance stabilization in my product? Well, if you could draw a resonance structure for that, I'd be really impressed, because there aren't any. So there's no way resonance can contribute to stabilizing an amine like that. Size. Is a nitrogen a particularly large atom? Not really, so I wouldn't really put size on there for that. Charge. Do we relieve a charge when we take off a hydrogen? I'll take a sip of tea while you think. We started off with this, and now there's nothing there. So, charge. So of those 5 factors for an amine, charge is really the only one that's going to play a significant role. Now, you could probably use electronegativity, because nitrogen is electronegative, and we're putting a lone pair of electrons on it. So you could say, yeah, that nitrogen's going to want those lone pair of electrons, but I mean, really, this one's going to be an issue with size. I'm sorry, with charge. Next question. Does the drunk squad have any questions? Oh, and let me pull up my email to make sure. Because I said I wouldn't really consider electronegativity for that, because we're not putting a negative charge on an electronegative atom like we do when we're talking about like alcohols or carboxylic acids when we deprotonate those. I'm just making sure nobody from class is trying to email me questions. Also, hello, Annie. Pardon me. I don't think you guys can hear that, but I hear my husband banging around in the kitchen, putting away dishes from the dishwasher. And he just keeps laughing. I don't know what he's doing down there, but it's apparently very funny. Just so you know, YouTube is free. You can create a free account. I can show you how if you don't know how, okay? It's okay. I'll take you how you are, Drunk Squad. Oh, sorry. Pardon me. Okay, I was looking at just the acid before any reaction. Yeah, I mean, you're kind of looking at the acid, but you're kind of having to think about it as the base, right? As the conjugate base. Like, what is it about it that stabilizes the conjugate base to make that reaction want to happen, right? Does the resonance structure that we have to make have to be like as stable as possible, or are we good if it is not the most stable? It's okay if it's not the most stable. At this point, I'm mostly concerned to make sure you guys know how to draw a resonance structure. I'm interested in having you be able to tell me that separation of charge is a bad thing. So those are options, right, for questions for resonance. I generally don't ask for more than one resonance structure per molecule because, you know, it's actually kind of an advanced concept that I don't want you guys like fretting over all the time, but, you know, it's important enough we need to kind of have a general understanding of it. I hope that makes sense. Still green. Thought I got the other color black back. Separation of charge is bad. Look, Annie was paying attention. So if you guys want to do some fun resonance structures, here's a molecule that would have quite a few options. If you're like, I would really like another resonance structure problem to work, there you go. And feel free to keep asking me questions. I'm just gonna... One of the practice tests you asked to describe a hybrid orbital is a good answer that electrons spread out, not to leave empty orbitals in the valence shell. What was the hybrid question? Decided negative carbon. It's one lone pair, meaning 2 electrons, yeah. So a hybridized orbital is, you've got a pretty good answer there. Electrons spread out, not to leave any empty orbitals in the valence shell, and they basically take all of the external, well, not all of them, but they take a variety of the valence orbitals in the valence shell and kind of average them out to make new orbitals. So you can get, you know, one s with 1p, one s with 2p, one s with 3p. So I hope that answers your question. More questions, keep coming. He's still down there laughing. One of the lone pairs to make a double bond and then be done. Are you saying just to make that? Like just moving the lone pair once? Yeah, so it just depends on the molecule. This has a hydrogen there, right? So if we move this pair of electrons onto there, you would end up with a carbon with 5 bonds, and we can't have that. Not only because we can't have a valence of 5 on carbon, but because we can't go past an octet. There's no shell that's going to be big enough for that on carbon. So you have to move it off of there, right? Who was it that was talking to me today? Nicole came by, right? I don't know if you're still here, Nicole. But she was saying, yes, can't forget those. But, you know, the thing that you want to do is to make sure that you're not forgetting your hydrogens. And so a lot of people, you know, it might be easier if you write out like a full calculus structure, or even like a condensed structural formula that would help you kind of make sure that you're keeping track of how many things are connected to that carbon. I understand that at this point, you're still so new to this that looking at the structures like I have on the screen right now can be a little bit challenging, right? And that's one of the shortcomings of the brief class, is because we are having to do things briefly. I have to give you guys like full immersion pretty quickly. But if you want to go back through and redraw those, like CH2 double bond, CH, right? This condensed structural formula doesn't take up too much room, right? Especially if you're, you know, working on it on an exam. And if you need that to make sure you get the right answer, absolutely do it. You know, and I'll give you guys scrap paper if you want it, etc. Oh my gosh. Are you guys seeing this? Can we like report that? Okay. Message reported. That was creepy. If any of you guys are getting really turned on by organic chemistry, I guess. All right. So if you prefer to look, if that might actually be 2 carbons shorter than I just had on the other molecule. Okay, I guess we get to block. This is literally the first time I've ever had a creeper come in the middle of an organic chemistry lecture. Like, who does that? And that better not be anybody in our class. You guys are being quiet. Ooh, that was a fun one. Look, we could go 3 steps in one. You don't have to go 3 steps in one. You could just do it, you know, one at a time, but can I draw a molecule with an amine and an alcohol? Sure. What kind of molecule do you want? Could be kind of anything we want. Amine, alcohol. How are those looking for you, Sarah? You gonna be okay, Onyx? Onyx is like 12 or 13 years old with mildly congestive heart failure, so she coughs periodically. I promise she's okay. She's right there in bed, though. That's terrible. Oops. Sarah, are you still there? Annie, why frowning? Oh, because of Onyx? It's okay, she's elderly. She's had a really long life, and a really good one. So, I try not to be sad about it. Unless you're sad about something else. I'm assuming you're talking about the dog. Casey, you reported the creeper. I also reported the creeper. Yeah. Thank you, dear. As I said, sometimes I'm just looking for basic answers. I mean, that question's basically just saying, show me what an amine looks like and an alcohol. So, I mean, you could draw anything you want on there. You could draw something completely ridiculous if you wanted. Like, we could have the world's largest molecule, or, you know. Let's put a ring in there, keep going. And as long as it has this on there, and that's an amine and an alcohol. Right? And if you were like, I want it to have a carboxylic acid, okay, put a carboxylic acid on there. At this point, sometimes I just need to make sure you guys know what certain functional groups are. And we're going to learn more of those in class on Friday, actually. Friday we'll start talking about how to name things, because we haven't talked about that yet. And some of these different kind of really important functional groups that you'll see a lot. Well, while I'm waiting on you guys to ask another question, I'll tell you the story. When I got home from work today, I went out... Oh, wait. sp hybridization of a ridiculous molecule. Sure, I can. Well, anyway, when I got home today, I had to go pick the garden, but it was raining. Because I garden, and it was raining. So, I went out... That looks terrible. Let me try that again. So, I went out and picked the garden, and then I look over... And I'm like soaking wet, and my hair's still wet from it. But all three of my dogs were on the deck staring at me. And they are soaked to the bone. Like, you guys are stupid. Annie, I'm not sure exactly what all you were wanting here, but I'm just drawing a ridiculous molecule that has some sp3 hybridized stuff on it, meaning those two carbons are both sp3 hybridized. Can I have a reasonable molecule, please? Let's look at this. And you guys don't have to answer this one if you're like either, you know, completely okay with this sort of thing, or So if you want to go through there and find the sp hybridized, sp2, sp3, unhybridized, you know, those kind of basic questions, there's a good molecule to do it on. I would strongly suggest you start by drawing out the calculus structure for that. Okay, so Casey, what would you like to know about acid-base reactions, honey? Can you be a little more specific? Do you just want an example of an acid-base reaction, or do you have one in mind, or like what type of, I need help from you is what I'm saying. sp3 or sp? Alyssa, I'm not sure what you're asking me, hon. The molecule I have there has sp, sp2, sp3, and unhybridized. Let's see. sp hybridized, there are 4 atoms. sp2 hybridized, there's 8. sp3 hybridized, let's see. Looks like 5. And I think there's 15 unhybridized. Oh, I'm sorry, Alyssa. Yeah, there's, and I think it honestly depends on how many people are using YouTube at any point in time, too. There's probably a lot of people using it at 7 in the evening. It's the best I can do right now. Believe it or not, the technology has improved significantly in the past about 4 years, because I tried doing this 4 years ago with a different platform, and it was really bad. Like, the video was always having to try and rebuffer and stuff. It just wasn't very good. So I'm kind of happy with how this is. I imagine another 4 or 5 years it's going to be spectacular with like almost no lag time at all. Casey, are you working on that acid-base problem? I put one at the bottom. Yawn. Sorry. Kaylee, was that you? I'm trying to remember. Yeah, Kaylee. Kaylee, are these the same answers you got? Oh, you're welcome, Sarah. Anytime. I used to want to do review sessions on campus, but you know, so many of y'all are non-trads or have jobs and stuff. It's just impossible. And then you have to try and find a room in the middle of the day. You know, it's about impossible. So I'm happy to do it though. You're slow? Okay. Is that just a general assessment of you in general, or slow at the particular problem? I have like 3 passed out dogs laying around me. I wonder if I can, don't be scared, I'm not removing anything, I'm just trying to make this bigger. Can you guys still see that okay? I'm just trying to give us a little bit more room to write stuff. I was happy using Kim's sketch, but it's still kind of hinky. I guess I need to maybe restart the program. On the right of the molecule, is that a carbon with a single bond to a carbon on the left with a triple bond to another carbon? Yes. So if we wanted to draw the calculus structure for that, or something similar to it, let's kind of combine it here to CH2. That's those two. That one is a CH bound to something down here. Looks like benzene. Bound to a CH2. That's that one. C double bond O. CH2. I'm like running out of room over here. And then a C to a triple bond to a CH. That looks terrible. Let me try and make that a little bit better. Yes, you can rewatch this. There's going to be a lag time, so the video has to process, and then it'll let me put it up. And it seems like sometimes the lag time is hardly any on that, the processing time, and other times it takes a while, but it should be up sometime tonight. Okay, so let me pull out some colors here. Let's see, let's do SP hybridized in yellow. So SP hybridized would be anything with a triple bond, right? So those two carbons have triple bonds, that carbon and that nitrogen. So you should have 4 SP hybridized atoms on that molecule. We can do sp2 with purple. sp2 would be things that you would expect to have a double bond. Now for us, we're making the assumption that oxygens are always going to hybridize the same way carbons do. So that's 8, the 6 carbons in the benzene ring, and then the carbon and oxygen double bound to each other. Then let's do sp3 as blue. So that would be 1, 2, 3, 4, 5. Yep, 5 carbons. And then unhybridized atoms are basically everything else left over, right? So anything that's a hydrogen or a halogen are the assumptions that we're making for this class. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Did I miss one? 6, 7, 9, 10, 11, 12, 13. Oh, okay. I counted wrong when I did that one. Okay. And then so, who was it that was it Casey? Want to do the acid-base reaction? So hopefully you looked at the nitric acid and said, that's a strong acid. That's nitric acid. That's on my list of strong acids. You saw the amine and said, wow, that's all the way up there in the 30s. That's not very acidic at all. So hopefully you looked at nitric acid and said, that's probably the acid, but even if you didn't know that nitric acid is an acid, it has a pKa below 0, so you know it's going to be a strong acid. So I'm going to do it this way. So nitric acid will donate a proton, giving us nitrate, NO3 minus, plus a protonated amine. So this was my acid, and it's a strong acid. This is my weak base. This is my conjugate base and my conjugate acid. And the pKa of the protonated amine is about 8-ish to 10-ish. Annie, did I answer your question about the triple bond? Oh, it's 7 o'clock. I gotta get going. One more question. Also, sorry about the pervert. I wonder if there's like settings I can use to like avoid that. So here's the thing. I do have my phone back now, so you guys can still ask me questions tonight. You just have to email me. Top triple bond is connected to a carbon. Yeah. So there's a carbon here and a carbon there. Because you have to have the triple bond to something, right? But then it only has 3 bond, right? No, because there's a hydrogen on it too, right? Because it's full of hydrogens unless you say something else. So you would imply that that hydrogen's already there. And you're welcome for helping you. It's been fun. You guys have asked some good questions. Is Casey still with us? Casey, did that acid-base problem make sense to you? I don't know if she's still there or not. Oh no, I don't know if you guys saw. I got new earrings for my birthday. Look. They're little Erlenmeyer flasks. Adorbs. Okay, Casey, so that doesn't make any sense to me because I don't know what isomer you're talking about. So without seeing the actual structures, I'm not sure. So if you want to work that out and then email it to me, that would be fine. And then I can answer your questions that way. That would probably be easier. We are kind of limited to text on this one, right? So if it's something that you could do a condensed structural formula, then that's fine. I could answer questions with that. But if it's got rings or something, we can't really do that. Fashionable in a cool, sciencey way. You know me. I do what I can. Anyway, well, I'm going to hop off here. Thanks for coming online and keeping me company tonight and not making me sit here by myself. That's always sad. I've had to do that a couple times when nobody showed up. And I just abandoned after about 15 minutes of nobody. But if you have more questions tonight, feel free to get back in touch with me. Email me. So like, Casey, if you're looking at a specific problem, I'm assuming you have a smartphone. I could be wrong. You're welcome, Nicole. But if you don't have a smartphone, just, I mean, if you can take a picture and send it to me somehow through email or Google Chat or Facebook Chat even, whatever's easiest for you to upload so I can see what you're looking at, that would be really helpful for me. Otherwise, I will be in tomorrow in my office. You're welcome, Annie. I'll be in my office. We usually have a meeting around noon, but we're not having it tomorrow. So before class, maybe around 1 o'clock, I could answer a couple of questions if you guys have anything last minute, if you want to come by my office around 1 o'clock. Okay? So email me tonight if you have questions, or take pictures so you can ask me questions about structural stuff. And then come see me tomorrow for last minute questions, or email me tomorrow. Email's a little bit harder during the day because I don't know when I'll have time to check it. But good night, everyone. It's been nice working with you. I hope you have a good night, and I'll see you tomorrow.